Okay, and we're back here now for those of you that showed up at 2 o'clock here. Thanks for sticking around. For those of you that have joined us since then, I want to welcome everybody to this special webinar feature today. My name is Miles Budimer. I'm the senior editor with Design World magazine covering motion control. And you are all here for the webinar, The Best Motor for Hybrid Electric Vehicle Powertrains. So we will get things going here. I'd like to give a shout out to our sponsors here on the page there, Bison and Maple Systems and PhD. Thank you very much for sponsoring today's webinar. A couple of housekeeping points before we get started. Everybody who did register for this webinar will get a copy of the webinar afterwards in their email inbox, but it also will be, you can access it at the Design World Online website, which is right there on your screen, designworldonline.com. Also keep in mind that we will have a Q&A at the end of this webinar, so if you have any questions at all, something that you think of during the course of the webinar, feel free to type it into the questions field there, and we will do our best to handle and answer each and every question at the end of the webinar. And lastly, if you're on Twitter, you can hashtag, you can tweet about this webinar in real time here at using the hashtag DWWebinar. So let me move things forward here. As I've already stated, I will be the moderator for today's webinar. My name is Miles Budimer. I'm the senior editor at Design World magazine covering motion control, and I'd like to introduce our presenters for today. We have two presenters. The first presenter will be Jay Schultz from Parker Hannifin, and the second presenter will be Brian Wisman from Bramo. Let me give you just a little bit of background on Jay and Brian. Jay holds a BS in mechanical engineering from the Milwaukee School of Engineering. He has spent his career at Parker Hannifin in various roles, including engineering, sales, business development, and product management. In his current role, Jay is responsible for bringing Parker's electric machines to market, defining new product platforms, and directing product engineering. He's written and contributed to numerous articles and has spoken all over the world on the topic of motors. So we welcome him and his expertise and knowledge. And our second presenter today will be Brian Wisman. A little bit about Brian. He holds a degree in industrial design from North Carolina State University. And he leads the Bramo design team with experience in both product and vehicle designs. His prior experience includes design work for clients such as Dell Computers, Omeda Medical, hope I'm saying that right, as well as race car body and aerodynamic design with Crawford race cars as well. So he also brings a very interesting background as well. So really looking forward to hearing Jay and Brian talk today. And so without any further delay, I will hand it off to Jay. And Jay, you can take it away now.
Thank you very much, Miles. Good afternoon or good morning to everybody out there. Appreciate the attendance. Today we're going to be talking about examining the differences in energy consumption primarily between permanent magnet motors and induction motors as they're used in hybrid vehicles. And so at the end of this presentation, you'll be able to get an understanding of which perhaps motor you would choose in an electric or hybrid vehicle powertrain. So today we're going to go a little bit over about me. I'm going to go briefly on that one because Miles did a great job. We're going to talk a little bit about Parker Hannifin and then the HEV platforms, electric motors, the usage cycle, and then draw our conclusions from there. So again, I'm an industry market manager. I lead the product management department here at Parker Hannifin for this initiative. I define the global marketing strategy and key business development initiative. You can find or connect with me on LinkedIn if you like. Feel free to check out my profile. Also, there's a QR code in the upper right hand of this slide that you can scan during this entire presentation if you want to download the entire full-length white paper for this particular topic. So Parker Hannifin is a pretty big company. We're $13 billion in sales. We have 8 distinct product groups, a lot of divisions. We cover tremendous amounts of markets in mobile and industrial, and we have 500,000 customers and 1 million products. So we're a pretty diverse, pretty large company. We fit into the automation group, and then within the automation group, we have a subset of that in the business units for vehicle electrification, particularly in my area, traction motors, integrated and belt-driven starter generators, and then auxiliary type electric motors for vehicles. So there's 2 real types of hybridization when Parker addresses it. The powertrain, and that's, of course, when electric motors are placed into the driveline to deliver power directly to the wheels to either replace or assist the engine. Another part of hybridization is on hydraulic equipment that drives excavator, shovels, or wheel loader buckets. Those types are perhaps removed from a PTO or from a pump directly onto the engine, and in place of that, a hybrid system is attached to that hydraulic system, so you can electrically power these hydraulic systems and reduce the loads on the engine. Same thing in a powertrain, except powering hydraulics instead of the wheels. So when we consider these 2 applications, the components of each of these 2 are very, very similar. This is an extremely simplistic diagram of a series hybrid, for example, but items 1 through 6 are standard no matter whether it's in a powertrain or electrohydraulic pump, and that would be generators, motor controllers, generator controllers, battery pack. The only thing that really changes between the 2 hybrids are whether you're driving the wheels or whether or not you're driving the hydraulic implements. So assuming now that we're talking about powertrains, when an OEM has an electric program, they have, in my opinion, 2 real major choices for their motors: induction motors and permanent magnet AC motors. Now, these 2 motors are very, very similar in a lot of ways. For example, their housing, shafts, they have copper, steel, electrical cables, all that. Those components are similar between the 2, including much, much more. The few things that differ, the major difference actually, are in the rotor inserts themselves. If you look at the rotor of an induction motor versus a permanent magnet motor, the geometry can be a little bit different between the 2. However, the major difference is in an induction motor, you have copper or aluminum inserts that travel axially down that rotor. And then in permanent magnets, you have rare earth material, rare earth permanent magnets that are essentially inserted inside of that rotor as well. So those 2 are the major differences there between the inserts. So the question is, what areas are impacted when exchanging copper bars for permanent magnets? Well, speed and torque characteristics are different. The physical size and weight are, of course, different. We'll see that in a little bit. Efficiency is drastically different. And then the big thing that sticks out in a lot of people's minds are material costs. Permanent magnets are much more expensive than induction. So that's a big difference. And then finally, the energy used over the driving cycles, not just the efficiency point at a single operating point, but all over the entire driving cycle. And so we'll look at that a little bit as we move forward in this webinar. So before we continue, I need to create a little bit of a fair scenario here. So we're looking at these 2 motors equally. And we're looking at a real-world application in this particular presentation and real-world requirements. We keep all of the hybrid system parameters and components constant. For example, the numbers that I said in a few slides earlier, the motor, the battery, the battery, the inverter, all that stuff is held constant between a comparison between these 2 motors. Particularly the voltage of the vehicle and the current on the inverter. These are held constant. And the battery pack itself and the capacity of the energy storage of the pack is held constant. So then we look at creating a permanent magnet AC motor and creating an induction motor that both meet the vehicle specifications given the constraints of voltage and current and battery. And then we compare the differences between those two motors. So I'm going to gloss over this, but as I mentioned, you can download this and get the more specifics. But the voltage is 600 volts. The continuous torque is 300. Current is 200 amps. Peak torque is 600 newton meters. Some of the vehicle specifications are a 4,800 kilogram vehicle. So this is like a small delivery truck. The rolling friction is known, the effective drag is known, the tire diameter is just short of a meter, and then we have a fixed transmission at the axle. So we needed to create the software methods to do this. So we did finite element models of this analysis so we could optimize both an induction motor and optimize a permanent magnet motor that would meet the previous specifications. A variety of operating points that we knew existed were looked at, and they were simulated and they were analyzed, and then we basically had to interpolate between certain points that were not actually calculated once we had enough points. So we ran thousands upon thousands of FEA simulations around this to really hone in on the right and correct solutions. We did have, of course, some assumptions, and the assumptions are that both motors run at the most efficient possible points within their operating zone. So slip was essentially adjusted on the induction motor to meet the maximum efficiency. That's not always used in real world, but when we're comparing efficiency numbers, we want to make sure that both motors were operating at the most efficient points. Both motors also have sufficient cooling to make sure that all the losses in the form of heat were evacuated from the motors, but they're not necessarily equal, the amount of cooling needs, because the energy usage is different in both cases. So looking at the speed and torque characteristics on the induction motor, which is the top, the bullseyes outline the operating points of the vehicle on both the torque curve on the left and the power curve on the right. So you can see that on the induction motor, we've got a product there that matches the customer's needs for both peak and continuous torque and peak and continuous power points. Same with the PMAC motor. We meet the peak and continuous torque requirements as well as the power requirements. And in fact, on the PMAC, you can see that power curve is actually extended a little bit beyond the customer's requirements. So looking at the physical size now of those two motors, once they meet the customer specifications, we look at the induction motor. The induction motor is a large diameter, 290 millimeters with a length of 234 millimeters, which gives us a total volume of 15.5 liters of volume for that induction motor. You look at the permanent magnet motor now, it's a little bit thinner, 200 millimeters, and then this happens to be a little bit longer, 326 total millimeters, so it's a little more slender of a motor. However, the volume there is only 9.8 liters. So we've got a significant reduction in terms of volume to be able to hit those torques and power points. Now, if you look at the electromagnetic efficiency, which I must point out that it does not include the mechanical losses in the system. This is just looking at the efficiency of the magnetic system. For the induction motor, it's a much lower efficiency across most of the regions, but the best efficiency is at low torque and high speeds. You can see that. On the permanent magnet side, very large sweet spot for the efficiency zone. It's lower losses at the peak, you can see along that region, and also the downside is it does have higher losses at low torque and high speed down in the lower right-hand side of that speed torque curve. From a material cost perspective of the active components, which is very interesting for many people, it's based on the actual procurement cost of this. We manufacture motors, so we use data that we actually have for this on purchasing. We didn't include any kind of labor or overhead in this specific calculation, nor did we amortize any tooling. But if you consider a permanent magnet motor as being 100% of the total cost of a motor that can perform this task, an induction motor's active components came to 74% of that active cost. And if you download the full white paper, you can see those two numbers broken out. I had to take these out in the interest of time. So induction is 74% of the cost of a PM motor. So our initial conclusions, induction motors takes up roughly 60% more volume compared to the PMAC. The permanent magnet, the PMAC motor, is 32% lighter. Max efficiency is comparable in terms of the actual number, a single operating point number, or of a region. Both of those meet torque and power specifications. The active material of the induction motor is, however, 26% less expensive, which is a big point. So our initial conclusion then is if size and weight are not factors, the induction motor seems to be a more attractive choice. Permanent magnet motors, however, are more attractive if weight and size are very important considerations. So moving on to the next area of discussion, what impact does the use of the product have, of each motor? Which losses are present at certain points becomes an issue. So for example, we're going to look at a couple of different points: low speed, high torque. For example, how does that look? Medium speed or mid speed, mid torque, and then high speed, low torque. So if we look at those 3 points, we might get a little bit of insight. We also want to look at the energy over a usage cycle and total losses consumed, whether it be a highly dynamic cycle like city driving, a low dynamic cycle like rural driving, or more of a constant speed like freeway driving. And those 3 will give us some insight. So we look at operating point number 1 and high torque. Those you can see it's roughly 600 Newton meters of peak torque on both of those, and less than 1,000 RPM. Total losses of the permanent magnet AC motor there is 6 kilowatts at that operating point. The induction motor, a whopping 17 kilowatts of losses. That's almost 3 times the amount of losses at that single operating point if you were to stay there. So with operating point number 2, we have a mid-speed, mid-torque, kind of in the mid-range of where that operating or of that speed torque possibility is. And on the permanent magnet motor, we're roughly at 250 Newton meters and 2,000 RPM, and the same point for the induction motor. And looking at the total losses at that point, significantly less, 1.2 kilowatts of losses for the magnet motor. And then on the induction motor, we have 2.7 kilowatts of losses. So at that point, you see the induction motor and the permanent magnet motor are coming closer. It's only 2 times difference now, 2 times more versus the permanent magnet motor. So this third operating point, high speed, low torque, pretty low torque output. This particular operating point for the permanent magnet motor yields about 1.2 kilowatts of losses, and for the first time the induction motor takes the lead at 0.9 kilowatts of losses. So in this scenario here, the permanent magnet motor actually has more losses than the induction motor and would be a less favorable choice at that operating point. So these 3 points give us insight into what to look for in the usage cycle. You know, we have to ask ourselves the question, how often does the motor change from one power point to the next? And then how drastic are those changes between the power points? And then how long does the application or the vehicle require the motor to operate at that specific power point? So the 3 prior points give us some insight in what we might expect. So now we combine those and we look at all this stuff here, all those points in a high dynamic drive cycle, which could be city driving, as I mentioned earlier. And this is characterized by very frequent changes in velocity. It also exhibits a pretty large amplitude from the peaks to the troughs of that cycle. And it also is a low to mid speed range of the motor itself. We're never really taxing the motor's overall RPM speed. And the tendency of this drive cycle is relatively short periods too. So we're going fast and then slow, fairly dynamically. And so that's a tendency of this type of cycle. So in this particular usage cycle here in city driving, the average speed is 7 miles per hour. The permanent magnet motor over this specific drive cycle consumes 3.4 kilowatt hours per hour. It's kind of a funky kind of a unit, but to get into seconds and all that stuff doesn't really give us a practical frame of reference. So when we talk about battery capacities, we talk about kilowatt hours, and so this is how much actually is used per hour. If you do the math, it works out. Induction motors over that same drive cycle uses 4.36 kilowatt hours per hour to accomplish this particular drive cycle. Now, as the cycle is repeated, the permanent magnet motor then would use 1 kilowatt hour per hour less of stored energy than the induction motor. And again, you can see some more details in the full white paper. The next cycle is a moderately dynamic usage cycle, rural driving, characterized by less frequent changes in velocity. The amplitude of this particular one might be a high demand, and it still are very high from the peaks to the troughs. However, they're not as frequent. This has a medium speed range of the motor, so we're not taxing it completely to its maximum extent. We have much longer periods between a change in cycles or in speeds, so we're not accelerating quite as often. And the average speed of this cycle is 30 miles per hour, so we're actually increased that speed quite a bit. So on this particular powertrain or this usage cycle, the total energy used in the vehicle for the permanent magnet motor is 14.2 kilowatt hours per hour for the PMAC, and on the induction, it's 14.5 kilowatt hours per hour. So at this point here, we're still at a little bit better energy usage consumption for this drive cycle. And as the drive cycle is repeated throughout the course of a day, the PM motor would use roughly a third of a kilowatt hour less per hour of stored energy. And then finally, the low dynamic usage cycle, or a freeway driving, constant velocity, characterized by very little or no change in velocity. Very small amplitudes between peaks and valleys. You could get behind somebody that's going slow, you change lanes, and you want to pass them, so you don't have a lot of aggressive acceleration, but it is a much higher speed range, specifically of the motor, of course, and the vehicle. And there are very long periods between a stop or rise from a 0 RPM point. The average speed here is 57 miles per hour. So again, we're taking it the next step farther in terms of vehicle speed and RPM. And again, this would be like freeway driving. And at this point, the magnet motor is 30.3 kilowatts of total battery energy used per hour versus the induction motor of 30.4 kilowatts. Now, these all include losses, and a big part of losses here is the actual friction losses of the air on the vehicle and rolling resistance. But still, in this particular example, if you dig into the details of the white paper, you'll see that the induction motor actually is more efficient. However, there's a weight penalty that goes into this vehicle because the induction motor actually weighs quite a bit more than the PMAC motor, so that's why it still just barely consumes a little extra energy here because of the weight, total weight of that motor. So the final conclusions here: Permanent magnet motors are more efficient over a dynamic usage cycle, which will, of course, enable then much lower energy storage costs. We're not talking necessarily about dollars of kilowatt hours that, when you plug in your battery pack. We're talking about energy storage. And what that means is a typical vehicle, depending on whether it's a micro-hybrid or a electric bus, can have anywhere from $1,000 to $30,000 to some of my customers have $200,000 of lithium-ion electrical storage. And so if they're using this dynamic usage cycle, and that's what they're modeling their vehicle on, perhaps they can use 35% less energy, and that has a profound impact on how much battery capacity they can reduce on their vehicle and still get the same amount of range, or they can just simply get 35% more range. And depending on dollars per kilowatt hour, it ranges drastically from $1,000 and up, but that could be as much as a $10,000 or $20,000 savings in a battery pack itself, which more than makes up for the difference in AC versus permanent magnet costs. So the PMAC would be a preferred choice when vehicle is very sensitive to size and weight, aside from the battery capacity issue. If the application has a very high or moderately dynamic usage cycle, and then if there's a large operating range of the motor that's required, the PMAC can perform a little bit better. However, the induction motors are better and maybe the preferred choice if all you're thinking about is upfront cost, 26% less upfront cost. And this is an issue if the battery technology may be a lead-acid technology, then it doesn't really make sense to invest because the lead-acid technology is very large and heavy weight anyway, and low cost. But that would be a key decision factor, decision point on that one. So applications with higher constant speed and lower power draw would be a more efficient use of an induction motor. Dynamic efficiency, if that's not a concern, then the induction motors can be kind of dialed in at a specific speed. And then size and weight optimization, if those are negligible design considerations of the vehicle, then the induction motor would be a good choice. And then again, as I mentioned earlier, a little bit more of a narrow performance band, the induction motor would work. So I thank you very much for your attention, and again, if you want more details, feel free to use your QR scanner and download the white paper.
Okay, Jay, thanks a lot. That was a very good presentation there, very informative and useful, I think. So I'll pass it on to Brian next. I just want to just put a word out there as well that if anyone does have any questions, if you think of any questions, you can go ahead and enter them in the question field there, and we'll try to see how many questions we can get to at the end in the Q&A section. So Brian, I think it's all yours now.
Okay, thanks, Miles, and thanks everybody for joining, and good job, Jay. That was a great technical presentation. My hope here is to provide some kind of a practical real-world application for case study of some of the things that Jay's discussed, and then introduce people to why Bramo has made the choice to use a permanent magnet AC motor on our vehicles versus AC induction motor. Okay, so Miles did let's see if I can back up one here. Miles did a great job introducing me. I know that many people may not know about Bramo, so I'll spend a little bit more time talking about myself and the company. Bramo is an electric motorcycle manufacturer. We've been building electric motorcycles since 2007. But we've been around since 2002, so we didn't always start as an EV manufacturer. I've been with the company since day one, and to prove that, if you look in the bottom left corner there's a photo of myself with a V12 powered supercar that we were developing when I first joined the company. We've come quite a long way from that point, and shifted our focus to pure electric vehicles, and specifically right now we're in production on 2 variants of electric motorcycle. The photo in the dead center is our first electric motorcycle prototype that kind of launched the company into this new phase of development. And I've participated in that development and our current product, which is called the Impulse, which is a higher capacity, higher performance electric motorcycle. And you can see on the upper right there, that's a picture of myself on my personal Impulse. So I kind of consider myself to be a super user of our products and enjoy working with our customers and providing feedback to our engineering team. As Miles mentioned, I'm not an engineer. I actually have a background in industrial design, but I've had the opportunity over the last 15 years to work with some great engineering groups, and so some of it's rubbed off, and I can speak to some of these engineering topics. I also have participated in managing our race effort and our race team at Bramo. So we participated in the very first electric motorcycle race on the Isle of Man back in 2009. There's a picture of myself with our rider there in the upper left. And although we went in as underdogs, finished as the top American team in that event, and really learned at how valuable the racetrack and the racing environment is for learning and developing technology. And ultimately, that's what led us to work with Parker and make some of these trade-offs and decisions that Jay has mentioned about which technology is the best to use in our pure electric vehicle. We do not build any hybrids currently. So just going through what makes up our electric motorcycle, I think for those familiar with electric vehicles in general, you'll see a lot of the same components. So I think it's very valid to whether you're looking at an electric car or electric bus or any other format vehicle, the componentry is relatively the same. So in the cutaway view, you can see we have a 9.3 kilowatt hour lithium-ion battery pack that sits inside the frame. We've got a motor controller that sits alongside the bottom of the bike and has a very short three-phase cable runs to the motor, which is the round gold piece, which is a Parker permanent magnet AC motor. You can see the phase lines there exposed. And then we have an onboard charger. Right now we have a 3 kilowatt onboard charger, which is the largest that you'll find on an electric motorcycle. A lot of the electric cars are now running 6 kilowatt onboard chargers, which I think is a good direction to go, and one that we're going to be pursuing in the future. But the point and the relevance in showing this cutaway view is to show how tightly packaged this vehicle has to be in order to make a respectable performance electric motorcycle. And so what we end up doing is versus an internal combustion engine vehicle, where most of the packaging is done around the engine itself, and then the fuel, being a liquid, is pretty easy to package in a variety of places. I mean, mostly it would be done in a fuel tank, but modern motorcycles also can package the fuel tank under the seat. Unfortunately, for a battery electric vehicle, that fuel source is not liquid. It's rigid, and it takes up a lot of volume. And so in this cutaway view, you can see how much volume is consumed by the battery and the electronics on board and the charger. And so to Jay's earlier point, having an application where size matters kind of leans you towards the direction of a PMAC motor. And in this case, the size definitely does matter, because the packaging room that is not consumed by our electric motor is being consumed by other components, namely batteries. For the foreseeable future, I think it's going to be a struggle to fit both a large enough battery pack and a large enough charger on board a vehicle to satisfy customer requirements. And so having a smaller, lighter electric motor is a pretty huge benefit if you're an OEM. Also, another point that Jay made was on the weight of the system. I would add that looking at the total vehicle, the other thing to consider is that with those increased cooling requirements and increased losses of an AC induction motor, you can assume that your cooling system is going to have to be larger, and these are water cooling systems, and so you may have to upsize your radiator, carry more water in the system, or have a larger pump, and all of that compounds the cost, complexity, and reliability issues you can have on a vehicle. So, sorry, the lag is causing me a little bit of trouble here, but backing up to how Parker and Bramo got in touch with each other and started building this relationship. As I mentioned, we went to the Isle of Man in 2009 and had a pretty good result there. We took 2 bikes to the race with a large version of our production motor, which was an axial flux permanent magnet machine that was not made by Parker, but produced about 50 horsepower, somewhere around 30 kilowatts peak. And unfortunately, one of our bikes did not finish that event based on the magnets overheating and demagnetizing. So we only were able to finish with 1 bike. We did pretty well there, and we learned a ton about developing technology for electric vehicles, so motor and battery. So we left that event knowing that we wanted to find a partner that knew more about electric motors than we did, and so we kind of scoured the globe and talked to a lot of different suppliers. I won't name all of them, but we looked at different motor topologies and different AC induction motors, internal permanent magnet motors versus surface magnet motors, and ended up working with Parker based on the fact that they had a right-sized motor for our application. At the time, it was called the MPT motor and was being developed, and they were interested, as we were, in putting the technology out on the racetrack in very high demanding use application in order to kind of harden it for the real world. And so we began working with them in 2010. Now, we selected the permanent magnet AC motor on the list of items here, but there is a good point of comparison because one of our competitors has chosen to go the AC induction route and has had reasonable success going that route as well. The reasons that we prefer the AC induction motor, so our bike is our racing motorcycle that we've had good success with over the past 3 years, is there on the far right, and then the AC induction motor competitive bike is shown on the left there. And the motors are highlighted in green, so should be apparent on the volume difference between the motors. The power output, peak power, is roughly the same. I'm being a bit conservative on our power figure. We're at the end of last year, we were seeing closer to 125 to 130 kilowatts, but roughly the performance level of these 2 motorcycles is pretty much equivalent. What we like about the permanent magnet motor is the reduced packaging size and definitely the reduced weight, especially on a high performance application. Weight is the enemy, and it's also the enemy for efficiency. We like the fact that the torque and speed characteristic of the motor supports either going with a direct drive or at least a single stage reduction gearbox rather than having to have a multi-stage reduction, which I think you can pick up in the competitive motorcycle image, that there's multiple steps in their gear reduction in order to get the speed range to the correct range for the rear wheel there. And then the lower rotor losses at high torque, which we see a lot of in a racing application, but also in a production street application where you're trying to provide maximum torque to get off the line, lowers overall your cooling system requirements. And then Parker has a unique opportunity with their permanent magnet design in that it's very flexible in terms of rotor length and diameter. And so we can find an application or a motor that is right size, perfectly sized for our application, and not find ourselves forced into developing a bike around a motor that already exists. Apologize again about the lag. So the pace of development for us has been very high over these past years, and it's not just on the motor side, it's also on battery development. So we're seeing the specific energy of the battery increasing quite significantly from 2009. If you look at the green bike on the left, that is our first production vehicle, and we had a 79 watt-hour per kilogram, 3.1 kilowatt-hour battery pack. And now we have two models, one with a 6.2 kilowatt-hour battery pack and one with the Impulse has a 9.3 kilowatt-hour battery pack, so 3 times what we were delivering to market in 2009. And all of that is obviously in the name of range. And so anything that we can do to provide the customer with the best range for the battery pack, that has to be purchased with the vehicle, because it's really what is the cost driver in the battery electric vehicle, the better off we're going to be. Some may wonder why the smaller red bike has a little bit higher specific energy versus the Impulse, and that's just a trade-off between specific energy and specific power. So the bike on the right has a little bit more power, and so we developed the battery pack to support that, whereas the bike in the middle is more of a commuter bike, and so we're maximizing specific energy and range, and we don't have to deal with as much thermal load on the battery itself, so that allows us to drive a little bit more higher energy density. And then at the bottom, we've talked about this already, is advancements made in racing. We've gone from an 8 kilowatt-hour, 55 horsepower vehicle that could maybe hit 100 miles an hour on a downhill at the Isle of Man to now a vehicle with over 14 kilowatt hours, 170 horsepower, and we were able to do over 170 miles per hour on the banks of Daytona in 2012. So what we've been able to do today is to commercialize the motor that was developed in conjunction with Parker on the racing program. And that motor in the top left is the assembled unit that goes into our Impulse electric motorcycle that's on sale today. We learned a lot of lessons along the way about efficiency and making sure that the motor has great continuous power as well as great peak power. And this motor produces about 42 kilowatts and weighs 35 pounds. So for a production motor, it has a very good specific power, and we've been very, very happy with it. And then we continue to push the limits with our racing motor, which is the second image there on the left, to develop higher and higher power levels in again, a very small compact package with some clever cooling techniques. We do include a 6-speed transmission on our production bike, but that is mostly due to the fact that we run at around 100 volt DC bus to make use of low cost inverters, and so the 6-speed gearbox allows us to create more rear wheel torque. And the graph in the bottom left shows a comparison between the blue is the rear wheel torque in each of the 6 gears on the Bramo Impulse versus the red, which is an internal combustion engine rear wheel torque for a 700cc V-twin motorcycle. So you can see that the area under the curve for the impulse is actually greater, and even though we have a motor that only produces, say, 60 horsepower, to the customer, the experience is that of a bike that has a much higher power level, because what they're actually responding to is the torque at the rear wheel. So at Bramo, one of the benefits that came from working with Parker was the ability to capture data on the vehicle while we were at the racetrack. And again, the racetrack provides a consistent, controlled environment where progress is easily measured. And since we have full data acquisition on board the race vehicles, but also our production vehicles, we can go back and do a lot of the analysis that Jay was showing, where we're looking at multiple drive cycles and determining how much battery capacity is being used, and how efficient the motor actually is in real-world driving conditions. And of course, this is all information that's shared with our partners like Parker. And so in that way, the technology keeps getting better and better, and with minor adjustments to magnets or to winding configuration for a specific vehicle, further efficiency improvements can be made. And this is how we continue to drive development of our products as we move from what is right now a pretty modular, flexible architecture in the product to more integrated architectures in the future, where you might say combine a motor controller unit directly with the motor itself in a combined housing, or something like that, or include a battery pack that is also a structural element of the frame. So through all of this, we've had great success with Parker on the Racetrack. In 2011, we got that MPT motor into a bike, and although it was only producing about 60 kilowatts or somewhere around 80 horsepower, we were able to capture the electric vehicle electric motorcycle racing season championship. Had some great battles with other technologies. Anything from a DC brushed motor was out on the track with us to an AC induction machine. And then in 2012, we were able to really up the ante and increase the power level on the motor and the full bike to about 120 kilowatts, which of course created more problems from a chassis standpoint, getting the bike developed to actually use that power. But we were able to wrap up the season as the champions again, and to take the world championship, which was run at Daytona, and put an extremely high load on the motor with the banking. Daytona, for those that don't know, is known as being just a grueling racetrack for even an internal combustion engine motorcycle, due to the high speeds and the high banking. And it was no different for us. We were one of the few teams that the riders could keep the throttle pinned on the banking throughout the whole lap, and not have to roll out to either protect the battery or the motor. So motor temperatures got very high, but we ended up taking the championship that year. And then last year, we also took they changed the name of the racing, but we took the championship again, our two bikes, and we were able to make some performance improvements on. We were able to deliver a little bit more current to the motor and make a little bit better use out of it. And we experimented with a new winding that we found was beneficial for longer tracks that benefited from moving the power curve a little bit higher in the RPM range versus shorter tracks that the big torque benefit of the permanent magnet AC machine really provided a big advantage, competitive advantage. that's really it. That's Bramo and our motor selection in a nutshell. So I'm happy to answer any questions in this next Q&A.
Okay. Well, thanks a lot, Brian, and thanks again, Jay, too. We've come to the point now in our, which is our Q&A. So just want to remind folks we do have some time there for some questions and answers. So if you have any questions for either Jay or Brian, excuse me, you can go ahead and put them in now, send them to us, and we can see what we can cover. Actually, there's I guess I can start with a few questions here. One of them may be, obvious or maybe not so obvious. I don't know, but and one of them is that basically we've looked at, and you guys have talked about two different types of motors really, and I was just wondering if there are any other motor types out there that you've looked at or that you've researched, and is it really just that these two are the best really for these kinds of systems, or not, I guess. So maybe we can start off like that.
Sure. I mean, I can answer that, and Brian can put his 2 cents in as well as Jay Schultz. There are, as Brian actually mentioned, they used induction motors, permanent magnet motors, as well as DC motors, DC brushed motors, and there are 3 technologies. There's also another technology called switch reluctance motors, which you find out there. But by and large, serious vehicle OEMs are trending towards permanent magnet motors. The Chevy Volt, for example, uses a permanent magnet motor. The Prius uses permanent magnet motors. The new Spark uses PMAC motors. So of the vehicles that are now rolling into the market, majority of them are PM motors. Some of the old historic, the EV1s out of GM were inductors, and we really find a lot of DC brushed motors that go into more of the hobbyist type products. One thing I want to point out too is that a major OEM that does not use permanent magnet motors is Tesla. And in the interest of time, I have my opinions on why they use that, so feel free to email me, and I will be happy to share my opinions on that.
Okay,
interesting. Brian, did you want to chime in at all, or?
Yeah, I definitely agree with Jay. When electric vehicles really kind of first hit the mainstream and we started racing, we did see some success with DC brushed motors. But as Jay said, it's really become more of a hobbyist solution. You've got brush dust and brush wear to deal with, and some thermal issues with a DC brush motor that make it really hard to use as a production application. And then there's some of the switch reluctance motors are interesting, but I've only seen them really considered for things like energy recovery systems and not for actual traction motor, because they typically don't have the power to do traction motor.
Okay. So this is another question that might follow up on this first question, but you had noted earlier, Jay, I think you talked about this. When you kind of looked at three different uses, you were kind of looking at city driving, rural driving, and freeway driving. I'm wondering about other types of applications, maybe vehicles on plant floors, or tow motors, or things like that, or even just other kind of short type of distance uses that aren't necessarily on the road, I guess. Would those kinds of applications still lend themselves to the permanent magnet AC motors, or some other type of motors, or how does that kind of play out?
Yeah, we see a whole lot of a cross-section of vehicle electrification, everything from jet skis to Class 8 trucks. And really what it comes down to, there are 2 major questions that need to be answered. One, what are your physical size constraints of the space that you have for your motor, and number two, what kind of battery technology are you using? Are you using lead acid, or are you using lithium ion? And no matter how big or small the vehicle is, if you're using lithium ion, because they are the single most costly component of a hybrid vehicle, it does the engineer, it pays dividends to investigate the permanent magnet motors efficiency on their specific drive cycle to perhaps reduce the amount of investment of, if it's a lead acid on a golf cart, well, you're not going to see the cost savings there by increasing the efficiency.
Okay. Maybe this is kind of a question for both of you guys, but in listening to both of your presentations, it really, maybe this is another obvious point too, but it really seems like the whole engineering question really revolves around the motor and battery technology, and it seems like those are, as the battery, as batteries get better, more power dense, I guess. Maybe there's some changes in the motor technology and vice versa too. Can you speak to any of that? I guess maybe even what you're seeing, what battery technology is, or which direction it's kind of headed in, and maybe what the impact of that is on the motors.
Yeah, I can provide a OE's perspective.
Okay.
We definitely do see. You're right. It's a complete system. The electric motor, the battery pack, and then also the inverter is critical for consideration.
Right.
And we don't really have time to go into it in this case, but there's some considerations: induction motor versus permanent magnet motor on the inverter side, and which has easier control. But what we see in the future is that as the batteries get better at delivering power, there are some architectural changes, tweaks that could be made to the motor to take better advantage of that. Maybe improve the power factor in terms of what's actually the power being delivered from the inverter, how much of it is getting to the motor and ultimately the rear wheel. So there's certainly some improvements in that area that I think are coming, but I would say that the biggest area of improvement needs to come from the battery pack.
Okay. Jay, you want to chime in at all? Or?
I think Brian did a great job of answering that. I couldn't add anything else.
Okay. All right. Sounds good. It does look like we're coming up to the 3 o'clock hour here now, so I think this might be a good point to kind of wrap things up here. So once again, I want to thank both of you guys, Jay and Brian, for your time today and for your knowledge, and for sharing that knowledge with us and our registrants and readers here. Once again, on that slide that you're seeing right now, you see all of our names there, and our contact info is there as well. So if you need to follow up with either Brian or Jay or even me, feel free to do so. Once again, everybody that registered for the webinar will get a copy of this webinar, and you can also find it at designworldonline.com. And you can connect with Design World through various ways there. I'm sure it's the same for you guys as well. But Facebook and Twitter and LinkedIn and Google Plus and all the other platforms that are out there. And also we can continue this discussion on engineeringexchange.com as well. So once again, thank you guys. Thanks, Jay and Brian, and thanks everybody for showing up today. And wish everybody a good rest of the day and rest of the week.
Great. Thank you, Miles.
Thank you, Miles. Okay.
Okay. Thanks a lot, guys. Thanks, Miles.